There's the one. Okay. On Tuesday, we went through some typical models of synchronous generators. We start from the most detailed model for round rotor, which has 6 flux linkage state variables plus 2 state variables from the swing equation. So totally we have 8 state variable for round rotor generator. And for cylindrical rotor generator, we can remove 1, so we have 7 state variables. Using the example on the right the right column, we show actually we can ignore 2 state variables, which are the side Q and the side D. They will generate some difference within the first maybe 0.1 second or 0.2 second, but it won't impact any stability study. So we can remove those 2 state variables, and then we will have the first pair of very useful variables models for the synchronous generators. For round rotor generator, it will be a 2.2 model, okay, with 4 flux linkage state variable plus 2 swing equation state variable. For cylindrical rotor generator, you can remove the last flux linkage, so only considering just 1 damper 1D in the Q axis. So it will be a 2.1 model. So the number before the dot, before the point, indicate how many flux linkage do you model in the D axis, and the number after the dot indicate the state variables of from flux linkage modeling the Q axis. Okay, so if we ignore the subtransient dynamic, which means we get rid of the faucet flux linkage state variable in each axis, so we're going to have 1.0 model and 1.1 model. And 1.0 model only has just few winding of flux linkage, which means for the flux linkage, we only just model D axis. We also call this model as one axis model. And so for round rotor generator, we can keep the flux linkage of the field winding and also for the first damper winding. So we're going to have a two axes to model. 1 from D, 1 from Q. So that's also called 2-axis model. So if you don't want to model any flux linkage, you only keep swing equation, that is called 0.0 model or classical model. So classical model can still model some dynamics about the inertia of the rotor or generator, but you won't be able to model anything from the flux linkage. Because the inertia constant H is also fall into the time frame of the subtransient dynamic. So you can still somehow model some subtransient, but even it's not accurate. But this can be very useful model when you want to create some new concept. Like if you want to design any controller or stability algorithm, you want to start from very simple model, you can start from a classical model. And then you can gradually add a flux linkage to this 1 or 2 step flux linkage to the state to the model, and to upgrade the model to 1.0, 1.1, or 2.1, 2.2. Usually 2.2 model is the most complex model you will be able to see regarding the power system stability. Okay, so in some other field, if we study protection, we study design of generator, they definitely can model the generator more accurately. So similar to what we derive based on the voltage equation, flux linkage equation, you can always go back to those equations. So if you do like electromagnetic transient stability study or simulation, you will need to go back to those equations because the model here are not accurate. Don't use those model for you like the EMT simulation, so they are not very accurate. Okay, unless you only want to do like approximate study. For instance, you have a power grid with a lot of single generators and also like renewable connected to the grid as inverter-based resources. You have a very accurate inverter-based resources model, like IBR model. But you also want to study how the generator interact with those IBRs. But your study is focused on the IBR, renewable, not on the generator. So you can somehow use like simplified model from this list, but you have to simulate in the 3 phases, okay? Maybe some reviewer will be fine with using those models as long as you don't want to study the detailed dynamic of generator, okay? But typically, when you need to go back to the very original detailed generator model. So we give this the whole journey starting from the very detailed model until very simplified model, but we haven't talked about the equations on those models. Okay, so we did show the equation from the one slide before this one. We show, okay, those are the flux linkage equations, voltage equations. So if you spell out those flux linkage equation and define like a state vector, and you can create a state space model in the form as the differential equation. If you add also power flow equation, that will be differential algebra equation. But those are not the model that the stability studies typically use. Stability study prefer some model. Each state variable has very clear physical meaning, okay? But if you take a look at the state variable here in that vector, so we know what the omega and the delta are, right? But do you know what the psi1d is? So if you simulate this generator, okay, it tells the 7D is oscillating and going to maybe become unstable. So what does that mean, really? Okay, is that important at all? Okay, you tell somebody, okay, psi1q is actually showing this dynamics. Is that interesting or not? That those are not good state variables for stability study. We want to keep omega and delta, but we want to replace those psi by something useful, like current or voltage or something we can interpret. Even that voltage or current are not an actual voltage current, but these are some fictitious things. But you still can study it, right? You can give some assumptions utilizing the engineering experience. So this is what we are going to achieve as the last step of this intersection. So we will need to derive a number of useful generator models for stability study. So which can match the different models here. So I will pick some of typical one to derive in detail, but I will leave some others as either homework or I tell you how to do it on your own, okay? So I won't be able to go through, I can go through from the AD model, 7D model to step by step to talk about the 2.2 model and ignore 1 to become 2.1 and go through all the process. But that can be very, take a lot of time, but I will leave some important step as homework, okay? But I will just show you the idea of how to do it. Let's go back to our original flux linkage equation and the voltage equation. Since here we can neglect the change on the psi d and the psi q, which are the flux linkage with the damper windings in D and Q axis. So we just simply cross off the derivative of psi d and derivative of psi q in the voltage equation. So those will be gone. Okay, so we ignore those two, but we still have a full state variable, which start with p. P is just a differential operator. Okay, our goal is to find a full differential equations for those 4 state variables, utilizing some parameter we derived. Okay, earlier, if you take a look at all the parameter in the flux linkage equation and voltage equation, they're like inductances and mutual self-inductances, but it's not very clear which one fall into which time constant. Which one is associated with transient dynamic, which one is indicating like a faster dynamic. But the one we derived from previous lecture, like SD SQ, SD prime, SQ prime, and double prime, and also like T single prime, T double prime, they are very clear to indicate which one is associated with subtransient dynamic, which is with transient dynamic. Okay, so we want to get rid of those L or M, but replaced by those X or T parameters. So this is our goal. So that 4 differential equations will be regarding the state variable, categorizing the flux linkage change, but all the parameter will be either X or T from here with single double prime. As I said, so we don't want the flux linkage to be the state variable. Definitely some flux linkage can be easy to interpret, like a psi FD. Psi FD basically just indicate the flux linkage of the field 1D. So if you do the derivative of psi FD, that somehow tell you how much field voltage is actually induced. But for some other flux linkage like psi 1D or psi 1Q, psi 2Q, what does that mean really? It's not that clear. So we want to introduce some useful state variable which are from the operating quantity. Operating quantity means any like quantity the operator or planar linear will utilize to understand the system condition, like voltage, current, power. Those are usually considered operating, also frequency. Those are operating quantity. So how do we do that? And we can get some idea by observing the steady state voltage equation. So we know that for the steady state voltage equations, we can have the equation about the ED, which is the voltage, instantaneous voltage in the D axis, and voltage in the Q axis. So X and R here are basically just the parameters. So the highlighted part actually together form an internal voltage, which we know is actually the EQ. But remember, how do we define the EQ? The EQ actually we define the second one to be EQ. But what is the first one? The first one is actually ED. Okay, so ED, EQ can be the real part, imaginary part of some voltage phasor inside of the generator. But for steady state condition, the real part is 0. Okay, and you only just have an imaginary part. So that's why for this internal source, you only just have an EQ. But you can assume there's a like voltage, internal voltage. I don't put any prime because it just indicates it's a steady state. So this is E tilde is somehow equal to like ED plus J EQ. It just ED is 0 for this case, for steady state. Okay. And then we will have this equivalent circuit. For round rotor generator, it will be an internal voltage and connected through some reactance. So for round rotor generator, the reactance will be either SD or SQ. If it's cylindrical rotor generator, it's better to take SQ. But if it's SQ, the EQ will be not accurately proportional to the field current. There will be some correction. We have talked about that. Then we'll get the terminal voltage. So the terminal voltage will be connected to the rest of the network. And this model is very simple and convenient because when we study steady state condition, we only just treat each source, each generator as an internal source connected through some reactance or maybe some resistance. So you can do the power flow study. So that's the model we have been utilized for power flow analysis, steady state analysis. Okay, so but our goal is to find a differential equation talking about transient dynamic and the subtransient dynamic. So can we borrow this idea to introduce another circuit, okay, describing the transient dynamic, and another one describing the subtransient dynamic. And the transient dynamic one circuit will utilize some parameter with single prime, and subtransient dynamic circuit will utilize parameters with double prime. So our goal is to find some internal voltage behind reactance model. Okay, so it may not be the same as this model, but it have similar structure, but taking different E and different X from the depending on what time frame we are studying. So for instance, we can have, for the sub-transient dynamic, we'll have internal voltage, we call it E double prime. We call it E double prime. And for transient dynamic, we have some internal voltage, we call it E single prime. And you see the E single prime will connect it to S prime. For round rotor generator, S prime is simply just SD prime and SQ prime. Okay. And the sub-transient dynamics, S double prime, and for round rotor generator is basically the same, SD double prime, SQ double prime. All right, so when you focus your dynamic study on a very narrow range of dynamic, let's say I only focus on sub-transient dynamics. So I can use the first one to connect it to the network and do all the calculation. So that is actually the model, the short circuit study people utilize. Because short circuit studies only focus on maybe the dynamic within the first maybe 10 cycle, 20 cycle, 0.1, 0.2 second, 100 to 200 millisecond time. So the transient dynamic has not started yet, and the system has not gone to the steady state. So they only just use first model. They have the same structure as the steady state model. It just connect the first model to the power flow, to the network, and solve power flow. That will give you somehow like a estimation about the fault current. Okay, and if you only study the transient dynamic, you can use the middle one. The middle one will have E single prime, S single prime as the internal voltage and reactance. Okay, from the example we know of the previous lecture, the S single prime is different from S double prime, and they are much smaller than XS. They're all different. Then you can imagine the E single prime, E double prime will be different, and they are very different from EQ. EQ will be just the imaginary part of E. E is the steady state voltage. Okay, so ready? So now we'll start going through this process, try to derive each one. So we start from the list of voltage equation, the flux linkage equation. Our first goal is to tell what this one is, E double prime. E double prime tilde as a phasor has real part, which is ED double prime plus J EQ double prime. And this is for the sub-transient dynamics. All right, so we start from the first two equations, talking about the ED and EQ. We just put those two equations here. And because the equation involves psi Q, psi D, and from the first two flux linkage equation, we can plug in those psi D and psi Q here. Then we'll get the second step. So those two equations basically just derived from the first two voltage equation and first two flux linkage equation. Then we compare with the steady state equation. For steady state equation, we know that the last item is basically just ED and EQ. Okay, so we are going to make some change on the two equations, two accurate equations based on the structure of the steady state equation. So what we can do is remove all the black part. Black part will be something we're already clear. So we'll keep those R anyway, right? So those resistance, we have no way to, it's pretty clear on the loss on the inside of the generator. So we keep that one. And for the blue part, we learn the structure from the steady state equation. And because we already defined the reactance in the Q and the DS is associated with the sub-transient dynamic. So we just go ahead to assume we learn from those two items and create those two items. So exactly the same, we only just add double prime here. And then we put this ED double prime, EQ double prime. So this one will have same structure as the steady state equations, and we just need to figure out a formula describing the ED double prime and EQ double prime. So SD double prime, SQ double prime already defined. Oh, if you use the hard copy from previous lecture, so I missed a minor sign here. So that's just typo, but you can easily tell. Okay, we move everything black on the left-hand side of equation, and the right-hand side will be something new, right? So we want to figure out. Okay, so next thing we can do is let's somehow guess what could be the ED double prime and EQ double prime. So ED double prime, if they represent some internal voltage in the D axis, it has to be related to some flux linkage. Okay, and in the same time frame. So if this sub-transient dynamic, it has to link to some flux linkage, because this voltage has to be induced by some flux linkage, also associated with the sub-transient dynamic. So what is that? Which one? This one I already tell you. So the ED double prime has to be from psi 2q. But why do I put psi 2q? Because take a look at those flux linkage. First of all, this ED double prime has to be induced by sub-transient dynamic state variable. And there are two sub-transient dynamic state variable. One is psi 1d, the other is psi 2q. Is that clear? Psi 1d is the faster one in the D axis compared to the field 1d. And psi 2q is the faster one in the Q axis compared to the first damper 1d. So those two are linked to the sub-transient dynamics. Which one should I pick? Because the voltage induced by flux linkage, by inducing, I mean, you do some like first order derivative of flux linkage to get voltage. So that make voltage be always orthogonal to the flux linkage. So if you want to find ED in D axis, you have to get the flux linkage in Q axis, which is the faster one. That has to be psi 2q. And you don't know they have exactly same number because they cannot. They are based on different units, so you have to put some coefficient here. So this is same. So psi q double prime, EQ double prime has to be proportional to psi 1d. Psi 1d is the faster dynamic in the D axis compared to the field 1d flux linkage. Is this clear? Yes. It has to be coefficient. It cannot be one. Okay. All right. So first of all, let's make it clear. So we have full state variable of flux linkages, right? We assume the first one, the psi 1fd and psi 1q, transient dynamic state variable, and the psi 1d and the psi 2q are sub-transient dynamic variables. Okay. And we assume psi d double prime is sub-transient dynamic. It's not influenced by transient dynamic steady state. It's just influenced by whichever here having the faster dynamic, the faster dynamic. So that has to be psi 2q, right? Clear. So next we move on. Then you just need to replace ED double prime by this item, and here is by this item, and then you can utilize the two flux linkage equation about psi 2q and psi 1d. So psi 2q will be the bottom one. So you have psi 2q is from here, and you have psi 1d is from here. So you plug in those two items in here in the parentheses. And next step, you just solve a K2Q and a K1D. You just go ahead to solve it. So you'll get, but that's another thing. So you need to utilize this equation. So those two equations will be true. They are the first two voltage equation. So you utilize those two equations because you compare this part. So that will be corresponding to that part. Okay. So voltage plus the voltage drop on the resistance has to be equal to all the blue atoms. So blue atom in the top two equations have to be same as all the summation of the blue atom in the bottom equation. So now you are ready to solve the K2Q and the K1D. That's easy. You just move the two items with parentheses to the left and move everything to the right. So you will get the formula for K2Q and the K1D. So this formula, those two formulas seem to be complex, but actually you can largely simplify the formula by utilizing the two equations here. Those two equations came from one slide in the previous lecture. We mentioned there are two ways you can model the time constant or for the transient subtransient dynamic or the radiances. But if you have some you take some approximation, and you will be able to get this very simple structure. I didn't explain why somebody liked this simple structure. So because they will be utilized here. Let me show that. If one that slice, where is that? Yeah, this is this slice. So when we explain the meaning of, for instance, SD single prime, SD double prime, compared to SD, LD, LD or SD. LD basically just the total of the leakage inductance and the stator winding inductance. And LD single prime, which means you add another field winding. You add one additional winding in the DICs from rotor, but that is faster. And that will somehow reduce the LD to LD single prime. And if you further add another one, the first damper one, you will make LD double prime. So compared to those three, you clearly tell how the LD change, right, from LD to LD single prime to double prime. And but in some this equation pretty simple, but it's not convenient to use. But they involve expression regarding the parallel circuits. So if you spell out the LD, LAD in parallel with LFD and L1D, that's very complex. That's a fraction. That's not convenient to use. So there's some other textbook they figure out. So if you make this assumption, that's not wrong. That's still pretty good, or at least at the same level of accuracy compared to this assumption, MR equal LAD. But if you make this assumption, that largely simplify those two equations to be only just have one fraction here. And so that make every inductance, no matter in D or QS, is in the exactly same structure. Okay, you can see this is like LD put some correction, and this is LD with some correction. And for the LQ, it's also LQ with some correction. So now you can tell. So if you want to calculate the difference between LD and LD single prime, basically just this item. So if you want to tell what the difference between LD minus LD single prime, so that's basically this one. If you tell the difference between LD and LD double prime, that's basically this one. Similarly, you can compare anything. You can compare LD prime and LD double prime. Similarly, you can do that for the QSs. So which means later, if you need such comparison, you want to tell the difference between the LD or LQ with different dynamics. So this assumption makes the formula much simpler. So here we're going to utilize this approach to make the derivation simpler. If you don't make this assumption, use the original one, it also gives you another set of model, but I tell you, it will have the same level of accuracy. With those two equations, K2Q is simply just equal to this one. Okay, you can verify that manually. Okay, you just plug in those two equations here. So now we know the psi D double prime is proportional to psi 2Q, and the coefficient is negative omega R multiplied by LAQ divided by LG. LG is actually self-inductance of the second damper winding in D acid, in Q acid, right? Okay, and EQ double prime is that one. Okay, so next one, which indicate, so we mentioned, so this ED double prime is induced by some flux linkage, but we guess that flux linkage will be proportional to Psi2Q. But if we have to give that flux linkage a name, we can call it Psi double prime Q, Psi Q double prime. Psi Q double prime basically just take this part. So you know Psi Q double prime, it basically just Psi D double prime divided by omega r and with negative sign here. In some textbook, they use Psi Q double prime as the variable. They don't use ED double prime. But if omega is 1, those two are basically the same. Definitely, if you don't worry about this negative sign, it just based on the definition on where the Q is. Some define the QS is to be leading D. Some define the QS to be lagging D. So between those two different assumptions, so there will be either with negative sign or no negative sign. But basically, Psi Q double prime is proportional to ED double prime. Okay, because Psi is not very clear about the meaning, but E is better, right? And also this Q can be very confusing. The EQ means the flux linkage in Q axis, but actually it will influence the voltage in the D axis. Okay, so I personally prefer using the ED double prime. Okay, so here the Psi Q double prime, Psi D double prime are just equivalent flux linkage, which induce the ED double prime or EQ double prime. Here is, yeah. This here should be Q. Okay, so which are similar to the Psi D and the Psi Q, which induce the EQ and ED. So if we go back to this circuit, so we know if we consider steady state, the inductance of the generator in DS is basically equal to this one plus that one. But if we start considering a transient dynamic, you need to add this one. You study the subtransient dynamic, you add this one. Okay, so that means that the total inductance will change. So for this subtransient dynamic, which basically means by adding some disturbance and look into the subtransient time frame, like 10 cycle, 20 cycle. So the total inductance is appear to be IOD double prime. Okay, and Psi Q, which is the flux linkage from the Q axis, it will be equal to like internal, somehow like an internal flux linkage in Q axis after some flux linkage loss due to this double prime L. So if you compare this one to somehow like to the Kirchhoff law of the voltage, this is like a flux linkage. There's some internal flux linkage. For this case, there will be a Psi D double prime. That's the largest flux linkage, and because there's a inductance, it will go through the inductance to a terminal, so flux linkage will drop by the L multiplied by the current, the terminal current, and the terminal flux linkage will be the internal flux linkage get rid of the drop on the inductance. Okay. All right, so that's how we derive for the E double prime. So now we go to the E single prime phasor, so which has real part ED single prime and imaginary part EQ single prime. So and their transient dynamic. So we start from the same two equations. So we also based on the steady state equation, we assume the same structure. Okay, so there will be internal voltage go through some internal reactance in the D and the Q axis, and then you get the terminal voltage in the D and the Q axis. So similarly, we can assume the ED single prime to be proportional to Psi 1Q, because psi1q is the transient dynamic state variable in Q axis, but it will induce the voltage in the D axis. Similarly, the EQ single prime will be proportional to psi FD. All right, so similarly, we do the same step. We move everything black on the left-hand side and right-hand side, and compare to the top two equation. Because here we have to assume the current in the second damper ending, the current in the first damper ending of the D axis, they have to be 0. So we ignore their dynamics. Okay, so now you can solve the K1Q and the KFD. And similarly, we can utilize those two equations to help us simplify the answer. And also we assume, yeah, so this will be basically just the solution. So when you solve the two equations in the box about the K1Q and the KFD, so the right part will be the K1Q and pink part will be the KFD. So, and you can also define the psi Q as psi Q prime will be the internal flux linkage in the Q axis, and psi D prime will be the internal flux linkage in the D axis. So there are some equivalent linkages, flux linkages that induce the E single prime. Okay, any question here?
Where is psi D prime? I don't understand.
Why is the psi D prime?
Which part?
Psi D prime is the internal flux linkage that can induce the EQ single prime. So based on those two, psi D single prime is the internal flux linkage that induces the EQ single prime. And from those two equations, we prove that psi D single prime is proportional to the flux linkage in the field winding, and the factor is this one. Is that clear?
Yeah, I understand the math. Is there any part like it you can show on the diagram?
What do you want to see on the diagram? You want to see a vector which indicates the flux linkage and
like L prime, L D prime, which part is like the whole is L D prime, and the whole is L Q prime. I don't know which part will induce like psi D prime. This equivalent diagram.
all right. So here, this equation tells the psi D single prime proportional to field winding flux linkage, right? So that's what they tell you. So what they are looking for?
That's the.
This is first of all, those single prime or double prime parameters are just fictitious things. All right, so they just for the convenience of study, because our goal is to create a differential equation with all state variable be somehow like operating quantities variables with physical meaning. So like for this case, if you focus on transient stability study, which means you can do system generator simulation, but you only care about the time frame from maybe 1 second to 5 seconds. So that's falling into the transient dynamic time frame. You ignore faster dynamic. So whatever happened in the first 1 second, not important. After 5 seconds, also not important. Then you can use this model. Then the E single prime will be important to you. Okay. So dynamic falling to that range will have some relatively constant voltage inside of the generator, which is just E single prime. And the projection to the DS is ED single prime. To the QS, it will be EQ single prime. That is the meaning. Okay, so next we're ready to derive the first generator model, which is 2.2 model. So here we're going to use ED single prime, EQ single prime, ED and EQ double prime at the state variable. So we know actually those single prime, double prime voltages are basically just proportional to the 4 flux linkages. Okay, depend on, but the Q and the D actually will have a 90-degree shift, which means the ED single prime came from the flux linkage in the QSs. Okay, the EQ single prime will be from the flux linkage in the DSC. We are going to replace all the variable here. At the end, we're going to only have voltage, readiness, time, and current. We don't need anything else. Definitely, you can also include resistance. Yeah, those all have the physical meaning. So those two are proved from the previous slides. That is the guidance to replace 7Q and 7D by the ED and EQ single prime. And those two also proved from early slides. We are going to replace Psi 2Q and Psi 1D. And we also want to make another assumption. If you don't do this in the final model, you're going to see an item like this one. Okay, but you just want to make it simple. You just call this entire thing as capital EFD. This one is proportional to actual field winding voltage. That's just for convenience of the final equation. Earlier, we have already definition about those single prime and double prime time constant. And we also have those equations. Those equations are based on the assumption we take just to make calculating the difference between the inductances of different time frame to be more convenient. So we'll take those equations. And those two actually are from the previous slides. When you're comparing the two equation, two voltage equation in the transient and subtransient dynamic, you can easily get those two equations. Another thing you can utilize is because so far we talk too much about the inductance, right? You may be more sensitive to see anything like a L, one L minus another L. But once you put everything in the per unit, so you can replace L by 2x because L and S are basically the same. So you can be sensitive enough. If you see this one, you see any formula like this one, you also keep in mind you can utilize this one to simplify any item with XD minus SD double prime. Okay. So which means here you have SD single prime minus SD double prime. You can take this one and that one. Those two together will explain what happened here. Is that clear? So you have the first one tell you the difference between LD and LD single prime. And this equation tells the difference between LD and LD double prime. So because this denominator want to find out the difference between the SD single prime and LD double prime, L can be D, L can be X. So they're basically the same in the per unit. So they together can contribute to either change or simplify that equation. Okay. I just gave you the final answer. There will be 4 equations. That's the only answer if you follow using all the formulas here. And your goal is to have only just T, capital E, and X. That's it, right? Also current. This is the final answer. And this is equivalent to the voltage and flux linkage equation together. I don't go through the detailed steps on how to prove each of them. I might already assigned the second homework. So in second homework, you may need to prove on your own. for some of it. But the last slides are the handout. So I just demonstrated how to prove one of the equation from the form, actually the most difficult one. So you can tell the idea how to do it, and finally you can prove that equation. So I don't go through this one in the class. All right, so next we can just bring all the equations plus two swing equations on the top, and also we add a number of algebra equations. See what algebra equation we add. The first bottom one is very easy. This one just tell you how to calculate the electric power. And this equation can replace that atom. Okay, so which means the P is not constant. P depends on both current and voltage at terminal. And those two equations basically just the first two voltage equation with a subtransient dynamic. Those two equations are new equation added. But if you take a look at the equation, it doesn't do anything. Okay, the left-hand side is just the definition of the terminal voltage and current as phasor. And right-hand side, it just tell that phasor can be represented by another phasor. So you have the voltage phasor, and it's similar to another voltage phasor, we call it EG, but the difference is only just changed by a certain angle, multiplied by an exponential function of like an imaginary number. So that an imaginary number will indicate some angle you want to change. So EG is same as ET, but it just measured at different frame. Okay. Similarly, you can have current also in that new frame. So EG and IG are basically just ET and IT, which are the same as the terminal voltage and current, but they are based on a common reference. Why do we need to consider a common reference? When you have many generators, you have to define a common reference. Okay, so the ET, IT for each generator in that common reference will be the EG and IG. So you need to change the angle. For round rotor generator, if you ignore the difference of the ED and EQ double prime, so you'll have this simple circuit, and that circuit is typically utilized for short circuit analysis to calculate the fault current. Okay, so this is summary of the 2.2 model. Okay, so next step, we're going to reduce the 2.2 model. Okay, first you can reduce the model to 2.1 model. So does anyone know how to change this one to 2.1 model? You only just take a single step. So what the difference between this one and the 2.1 model? Right, can be ignored. What do we do to change this one to 2.1 model?
Ignoring it.
Ignoring which? First, okay, so we have four equations, right? They categorize the four flux linkage state variables. Those two are transient dynamic, so we need to keep those two, right? At least, because when we see 2.1 model, we have two state variable in the D axis and one state variable in the Q axis. So this is D, this is Q. So which means for the D axis, we need to keep both equations. So which two equations are for the D axis? Where should we tell? Which one is this one? Does this one belong to the D axis? Yes. Don't be confused by this sub, right? Take a look at that one. Because you need to recognize time constant. Those two are from the D axis. The other two from Q axis. Don't look at the subscript of the E, because the true state variable is actually the flux linkage. So we need to keep the both equation in the Q axis, but for Q axis, for D axis, but for Q axis, we only just keep the slower one. the faster one will be removed. But by removing, I don't mean you just cross off this equation. No, if you cross off this equation, you mess up everything. Because how do you reduce a differential equation? It's not like you just forget that differential. You basically make that time constant be 0. That's what you do to eliminate a differential equation. So still keep the algebraic part. So this one will be 0. So what you need to do is you assume the last differential equation to be 0. And that becomes an algebraic equation. So by using this one, you solve the ED double prime. Or maybe whatever you needed higher. Like here, I still need ED double prime, right? You still need to tell what this one is. But now from the bottom equation, you can solve the ED double prime and eliminate ED double prime. Okay. So the 4 differential equations on flat linkage become 3 differential equations plus 1 algebraic equation. Then you get 2.1 model. So to change this one to a 1.1 model, what do you need to do? You just get rid of the second. Oh, sorry, it's not this one. It should be another single double prime. So this is still here, but you need to get this one, which means let's just make it clear. So you make this one be 0, this one be 0. Then you get a 1.1 model. Okay, so using the last 2 equations to solve the EQ double prime, ED double prime, and plug into the third and the fourth equation to eliminate ED and EQ double prime. Then you have only 4 equations with single prime parameter. So that's the answer. So you won't be able to see any double prime parameter. If you want to draw the block diagram, the swing equations we already explained, so it will contribute 1 block diagram with 2 state variables. And the next 2 differential equations can create another 2 block diagram in Q, one in Q axis, the other in D axis. That's why this model is also called a 2-axis model. Okay, so they will have such block diagram. But you can see I treat the damper winding current in the D axis and the second damper winding current in the Q axis still as input to this block diagram, because those 2 block diagrams are obtained from not from this 1.1 model, actually from a 2.2 model. So if you try derive the block diagram not from this slides, but using the previous slides equation, you try to derive the block diagram for this the first equation and the second equation on the flat linkage, you will get a very complex block diagram. But if you somehow simplify it, eventually it will become this one, those 2. So you put everything related subtransit dynamic will into the I1D and I2Q. So this one just explain. So the subtransit dynamic can be considered as some faster, some input carrying faster dynamic into this model. And the main time constant for this model is still the single prime parameter. So this is like 1.1 model. So if you further get rid of the second differential equation on the flux linkage, so you will have 1.0 model. So which means here you just make this item be 0. So this entire box become just 1. Okay. So the second block diagram will basically become algebraic equation. So here we'll make this one be 0. This one will be gone. Okay. Then you utilize this algebraic equation together with the 3 differential equations that will give you a 1.0 model, which is the 1-axis model. Okay, they're clear. So for this model, you have internal voltage, which is the E single prime. Okay, so I will go through some signal readings and some resistance and to the terminal. Okay, next slide, I'm going to draw a phasor diagram based on all the three set of equations. So we start from the steady state equations. So that equation will have internal voltage, which is EQ. So here we can, because we want to make a Q axis to be imaginary axis, and D axis to be real axis. So we'll always draw the EQ as the Y axis here. So this is a phasor diagram. So we put the EQ is actually in the Y-axis, and the D is X, which is the real axis, and we assume IT which is terminal current, will have certain angle. Okay, some angle we don't know, and also we have ET, which is terminal voltage, leading the current by some angle. So here we assume the generator is driving some lagging power factor load. Okay, so if the external load is leading power factor, so the E will be lagging I, but you can draw another phasor diagram. We just use this one as one example. First, we draw the phasor diagram for steady state condition. So how to draw that phasor diagram? So we start from the head of the ET, and we draw a little phasor, which is in parallel with current. So this one represents the voltage drop on the resistance. So usually this part could be very small. And this is in parallel with IT. Because resistance doesn't change the angle, it's real. And next, we need to draw the voltage drop on the signal readings. The signal readings is completely imaginary, right? So you need to draw a phasor which is orthogonal to the current, okay? Leading the current direction by 90 degrees. So you draw this blue large arrow. Okay, that one defines the final EQ. So this is phasor diagram for the steady state condition. To draw another tool, we have to, because for this case, we want to consider a more general case, right? So it's not round rotor. It can be round or ceiling pole rotor generator. For round rotor generator, maybe the ISD, SQ are not exactly the same. So here we have to consider the current component separately in the D and Q axis. So which means here we need to, we assume there's a little phasor. This is, we call it ID tilde, which basically just the length of the real part of the current, but direction is the same as the D axis. And also in this direction, there's the IQ tilde. Okay, they're basically just two components. Similarly, for the voltage, you can consider maybe there's a ED. Don't call it AD. Just maybe it can be confused with the early eternal voltage. Let's just define those two current. But you understand, the voltage will also have a component in the okay. So the projection to D axis will be the ED, right? And projection to the Q axis will be EQ. But I don't draw it just to avoid confusion. Okay. So now, to generate the phasor diagram for transient dynamic, we're going to utilize SD and SQ single prime. So this part is still same. And starting from here, the next one I need to consider voltage drop due to the SD single prime. So SD single prime from this equation is multiplied by the ID. Okay. So it needs to be multiplied by the phasor, capital ID tilde. The capital ID tilde is basically just phasor of the ID. And this one will be orthogonal to D axis, right? Because there's a J here. the next voltage drop will be on the SQ single prime. SQ single prime multiplying IQ. So you need to draw another phasor orthogonal to QICs. So it will be this one. So then the end will define the E single prime. Similarly, you can do that for a double prime phasor diagram. When I draw this phasor diagram, I intentionally to make the head be not on the same line. Okay, so regularly speaking, the height of those three voltage phasors are not on the same straight line. So they can be on the straight line if you ignore the saliency. If all the radians in the D and Q are equal, okay, then they may be on the straight line, same straight line. But in general, they are not on the same line. And also, you know, the capital EQ tilde, which is the internal voltage of the steady state circuit, the longest one, right? And the E single prime is shorter, and the E double prime is shortest. But they are all longer than ET, the terminal voltage. But this is not always true. It depends on the field voltage. Because generator, you can have exciter to change the field voltage. So if the field voltage decreases, the EQ will decrease. Especially when you have the lagging power factor. When you have lagging power factor, the generator is generating both IT power and reactive power. So internal voltage typically will be higher than the whatever voltage outside the generator. But if it's a leading power factor, you can try. If you want, you can draw another phasor diagram with IT to be leading the ET. So the length of those three internal voltages may be different. Okay, next I want to explain the common reference. So what common reference means, there's another reference which is different from D. So let's just assume this is the common reference. So this common reference is pointing to the same direction for all generators in the same system. Okay, so it's not just for convenience of any single generator. It's actually, you can arbitrarily pick any direction to be the common reference. So we pick this one to be common reference. What are the voltage and current in the new reference? So the phasor direction is still same. So this ET is still that one, but relative to the common reference, this angle will become smaller. Okay, so how can we know the new angle? We can utilize two angles. One is this delta I is actually defined as the internal rotor angle. That is defined to be the angle between the terminal voltage and EQ. Okay, and we tell, so delta I is actually not the rotor angle. It's actually the internal rotor angle. But rotor angle is defined to be the angle relative to the common reference. So if we know this axis to be common reference, and this angle will be delta. Okay. So this part is really the delta. Then what is this angle? This angle will be 90 degrees minus delta. This little angle. So the common reference, the angle between the common reference and the D axis will be 90 degrees minus delta. So which means if we know the value of the ET and IT in the original frame, but we want to translate to the new frame, we only need to shape that angle. We reduce the angle of ET and IT both by a little angle. That angle is equal to 90 degrees minus delta. So which means we can use this rotational transformation. So this transformation just decreases both ET and IT by a little angle, and which is equal to that angle. Okay. So yeah, so this transformation ensure you can still utilize the equation we derived here, because when we use the model, or either not this model, let's put the more complex model, we call each quantity to be associated with either the Q axis to D axis, but that D and Q is based on the reference of the terminal voltage. Okay. But when you have many generators, it's not convenient. By modeling, when you model your generator, you consider common reference. You just don't worry about that common reference. You still model everything in the internally based on the terminal voltage. And then you calculate whatever ET and IT. But when you connect all the generators together through power flow equation, the voltage current in the power flow equation need to be EG and IG with the angle shaped by that little angle. Otherwise, your calculation won't be correct. Okay. It is clear? So if you want to program a simulator to simulate many generators in the same system, not just a single generator. If you simulate single generator, single machine InfiniBus system with single generator, don't worry, you can make this terminal to be the reference. But if you simulate 3 generators, you have to define a common reference. The one thing you can do is you may make maybe one of the 3 generators to be the reference. Then for that generator, you don't need this transformation. Okay, but the other 2 will need that transformation. The other 2 will need to correct the angle by shifting that amount. Yeah.
Is that delta? That's not
Delta minus 90 degree. Yeah, delta minus 90 degree. Yeah, delta is actually the delta is here. But in this equation, it only just utilize differential delta. So this is the only part you need the actual delta. But the actual delta has to be defined based on common reference.
not delta I.
Actual delta is based on common reference. It's defined here. You have to first define the common reference. Then the Q axis leading to the common reference for each generator will be that delta. But this common reference itself is not important. You can define anyone. For instance, if you make this generator itself to be the common reference, you make the DSC to be the common reference, the delta will be 90 degree, right? Okay. Or you can make its terminal voltage to be the common reference. That's fine. So for this generator, the delta will be delta I. But the other generator will need to utilize the same reference to recalculate the delta. And using that delta, you can translate between the values on its own to the value in the system. Then use that EG, IG for the power flow equation. So the power flow equation can be correct. Okay. All right. So if there's a round rotor generator, if we ignore salient pole saliency with salient pole rotor generator, so all the head of the E double prime, single prime, EQ will be on the same straight line. Because you can use just single reactance to explain what happened for the subtransient dynamic, which is similar to the transient dynamic as well. Yeah, that's my last slide. Okay, what else? Maybe there's 2 additional slides I can quickly talk about. The first one is this one. This is from the PSSE software manual. So on that software manual, they give you some typical models which are commonly used by most of the power companies. So you can tell from the name, like GENS, GENSEL, that stands for like generator, salient pole rotor generator. This SAE, if you check the manual, there's some detailed difference between those 2, maybe the different type of salient pole rotor generator. I think E stands for some excitation feature different. Okay, so those are the round rotor generator. Okay, and this is a classical generator. So for classical generator, you only just need to provide steady-state reactance and XD single prime. You don't need any other parameter. Round rotor generator is actually the most detailed model. You need to provide all the information. This one may be too small to the student in the back, but I want to show you one snapshot from the menu. I think this is the Gen cell, which is a ceiling pole rotor generator. So for ceiling pole rotor generator, that's the most accurate model will be 2.1. So you have a two-state variable in the DSCs and a single-state variable in the QSCs. So this one gives you a detailed block diagram. So in the QSC, you only just have one integrator, one state variable. So that is the TQ0 double prime. Okay. So those are some algebra equation you're going to utilize, which is same as the bottom equation I showed earlier on my slides. Yeah, if you tell this equation, that's exactly I show how you can change the quantity from the internal reference to the common reference. So delta will be based on common reference. So you need to do this correction of the angle. You can just Google the name of the model. I believe this page can be open. You can easily get access to this page. On the right column will be the round rotor generator. So compare to the ceiling pole rotor generator. So you have a two-state variable here. You have both ED single prime, and in this specific software, it doesn't call the double prime. It call it just PsyQ single prime. A little bit confusing, but this one is corresponding to our ED double prime. Okay, so the second state variable in the DSCs, they call it it's ED single prime. So naming is a little bit different, but if you want to derive the equations based on the block diagram, it's not hard. You're supposed to have the capability to write down the differential equation based on the block diagram. And if you compare that differential equation to what we derived in the class, they're pretty same. Okay. All right, so yeah. Okay, that's my last slide. Okay. All right, so next week we're going to start the section on the load modeling.